You don't need a probability degree to do NLP. You need to be comfortable with one idea: P of next word given previous words. Everything else in this video builds directly from that. And I mean everything. GPT, Claude, LLaMA, spam filters, speech recognition, all variations on that single line. So today, the bare minimum probability. 6 concepts. Read them once, they stick. And then one practical trick. LOD probabilities. That saves you from numerical disaster the moment your sentences get long. Last video was FSMs. Pure category logic. Is this string in the language, yes or no? Binary. Today we soften that. Instead of yes or no, we ask how likely. That single move turns FSMs into probabilistic language models, and that's the whole story of NLP after 1990. The puzzle. If probability is such a big deal, why is the actual math so small? Answer. Most of what you need reduces to counting events divided by total events, and a few simple rules for combining probabilities. That's it, the rest is application. Today's 3 beats. First, the foundation. Sample space, random variables, joint and conditional probability. Second, the combiners. Independence, chain rule, marginalization, 3 moves that let you build any probabilistic model. Third, log probabilities. Not glamorous, but if you skip this, your language model overflows to 0 and dies. Beat 1. Sample space, the set of all possible outcomes for a coin, heads or tails, for a die, 1 through 6. For a language model at position 17 in a sentence, every word in the vocabulary. 50,000 outcomes, easy. Random variable, just a name for the outcome we care about. If we call the next word X, then P of X equals cat is a probability. Simple. Joint probability, P of A, B. The probability that both A and B happen. P of it rains, and you brought an umbrella. In NLP, P of the word cat and the word purrs, both showing up in the same sentence. Conditional probability, P of A given B. Given that B happened, what's the chance of A? P of purrs given cat. That's the base unit of every language model. The relationship between them. Joint equals conditional times marginal. P of A and B equals P of A given B times P of B. Read that out loud. The chance both happen equals the chance A happens given B times the chance B happens. It's the algebraic pivot that unlocks everything else. Bayes' rule falls out of this. The chain rule falls out of this. Learn it once. Beat 2. The combiners. Independence. 2 events are independent if knowing one tells you nothing about the other. P of A given B equals P of A. Rolling a die then flipping a coin. Independent. The words on the and co-occurring, not independent. In NLP, almost nothing is independent, which is why we need conditional probability everywhere. Chain rule. The general form, P of a whole sequence equals a product of conditional probabilities, each one conditioned on everything before it. P of a sentence equals P of first word times P of second, given first times P of third, given the first 2, and so on. This is exactly how autoregressive language models work, word by word, each conditioned on the past. Marginalization. You have a joint distribution, but you only care about one variable, sum over the other. P of A equals sum over B of P of A, B. In NLP, you have P of word given topic, but you want P of word alone, sum over all topics. Marginalization is the workhorse of Bayesian NLP, and it's just a sum. Beat 3. Log probabilities. Why they exist. Take the chain rule for a 100-word sentence. That's a product of 100 numbers, each less than 1. Tiny times tiny times tiny, 100 times. You get something like 10 to the minus 200, which underflows to 0 in floating point. Your model just told you this sentence is impossible. It isn't. Your representation is broken. The fix. Take the logarithm. Log of a product is a sum of logs. So instead of multiplying 100 tiny numbers, you sum 100 manageable negative numbers. Log of 10 to the minus 200 is minus 460. Sits comfortably in floating point. Every language model in production ranks in LOG space, not probability space. One more benefit. In log space, ranking is the same as in probability space. The most probable sentence is also the highest log probability. So all your scoring, sorting, beam search, everything works in log space, and your gradients from training don't explode. Log space is not just numerical hygiene, it's how the whole field actually runs. 3 takeaways before the quiz. 1. Joint equals conditional times marginal. P of AB equals P of A given B times P of B. The whole pivot. 2. Chain rule turns a sentence into a product of conditionals. Autoregressive language models are chain rule in code. 3. Always work in log space. Products underflow. Sums of logs don't. The whole field runs in log space. Quiz 1. What does the chain rule of probability say? A joint is the sum of individual probabilities. B, a whole sequence probability, is a product of each item conditioned on the past. C, all events are independent. Or D, conditional equals marginal. B, sequence probability is a product of conditionals. That's exactly how autoregressive language models, GPT, Claude, LLaMA, score sentences. Word by word, each conditioned on everything that came before. Quiz 2. Why do NLP systems compute in log probability space? A log is faster than multiplication. B, to avoid numerical underflow when multiplying many tiny probabilities. C, log probabilities are easier to explain. Or D, the math requires it. B, underflow. Multiplying 100 numbers each, less than 1 drops your product to 10 to the minus 200, which becomes 0 in float. Take the log, and multiplication becomes addition. Manageable negative numbers, same ranking, safe. Quiz 3. In NLP, are words in a sentence typically independent? A yes always. B, yes for languages other than English. C, no, words are heavily dependent on previous words. Or D, only vowels are independent. C, almost nothing in language is independent. After the cat sat on the next word is overwhelmingly mat, floor, or chair. Independence is a special case. Conditional probability is the general rule, which is why we need it everywhere. Back to the puzzle. Probability for NLP is small because most of the work is counting events, then combining with conditional times marginal. Add log space, and you have every language model that has ever shipped. Simple foundation, deep application. Next video, the man who turned probability into information. Claude Shannon, 1948, and why English has 1.3 bits per letter. Next time, Claude Shannon and entropy. In 1948, he invented information theory. In 1951, he asked how predictable is the next letter of English. The answer? 1.3 bits. Set the entire course of NLP. 9 minutes, real math. Hit subscribe.